Hello, and welcome to this session recording from the AWS Summit London 2015, focusing on how to scale the platform for your startup on AWS. My name is Andreas Chatzakis, and I'm a solutions architect at AWS. Before we get started, if you would like to download the slides from this session, please check the video description for a link to the slides on the AWS SlideShare, where you can view and download the slides. You might be watching this video because you're a member of a startup team, or you simply have an interest in scalability. We're not only going to show you some generic design patterns today. I'm going to try to walk you through a typical journey of a startup for an architecture and describe a pragmatic approach tailored to the realities of startups. And how is a startup different? A startup is like a race where you have a limited window for a potentially large opportunity. You have a small team, but you don't have any legacy to slow you down. You want to be able to focus on features and not on over-engineering. But you also want to commit to smart technology choices right from the start, so that you don't have to re-engineer within a few months. And your biggest fear will be that your business model is successful, but your technical platform cannot cope with that. That would be very bad indeed. So let's avoid this by building a scalable architecture for our startup. A scalable architecture can grow without practical limits simply by adding more resources. An efficiently scalable architecture is even better, in the sense that it will also help us reduce the cost per user as the startup grows. This is a good objective to have. But let's start from day one. Perhaps there are a couple of developers working on their idea, and they're going to need a server to host the application for testing and sharing with some friends, family, or some early enthusiasts. Signing up for AWS and launching an EC2 instance is a few clicks away. You can set up that single server, an EC2 instance, to test your code and run a private beta. You install perhaps a database engine and your web server of choice. You upload your application code and you're good to go for now. Soon you will want to open access to the wider public, and you will run a public beta. If things go well, you will soon need a bigger server, and that is easy on AWS. You can add more and faster storage with EBS, and you can stop the instance, change the size of your instance, and start it again with perhaps more RAM or CPU. Of course, that is not our long-term strategy. This will eventually hit an endpoint. Plus, having everything in a single, very large server is not great in terms of fault tolerance or cost efficiency. So as a first step, let's go ahead and move the database to its own dedicated instance. We have 2 servers now, so instantly a lot more capacity. But we can also select a different instance type tailored to its workload. Perhaps your database would benefit from a lot of RAM, so we can try using an R3 instance for that. This is also better in terms of security. For example, we can really lock down access to the database server. And this is usually the point where someone will ask me, which database should I use? And there are 2 main types of databases that are popular: relational databases and NoSQL databases. And my default answer is that you should probably start with a relational database. There will be exceptions, and later on we will talk about those and how those 2 technologies scale. But relational databases will work well for most applications. They offer more features, and there are more developers out there that have experience writing applications for them. So start with that, and the reality will be that later you can always add NoSQL for the right workloads. And you could be installing your database on an EC2 instance and managing it on your own. But we know from experience that relational databases are hard to manage, especially at scale. Poorly managed databases are a leading cause of downtime in the IT world. This is especially true for startups with limited resources. You're not going to have access to consultants to help you build a robust database layer. Hopefully on AWS, you don't have to deal with that problem because there is the Relational Database Service. And RDS is a service that can solve that problem for you. With a few clicks, you can have a database server running MySQL, Oracle, SQL Server, or Postgres. And AWS is now going to handle all the provisioning, hardware replacement. It will make it easy to migrate to a larger server when you need that. It will handle the backups, the security patches, etc., so that you can power your application with a robust database engine. Now we could start scaling those two tiers straight away. But let's take a step back and implement some quick wins early on in the process. These are some low-effort changes that are going to give us a lot of breathing space and cost efficiency as we grow. First, we want to store any static assets like CSS files and images on Amazon's Simple Storage Service, S3. S3 not only stores those files, but it can also act as a highly scalable hosting service. Instead of serving those assets through your web server, you offload this task to S3 URLs. This is going to reduce the load for your web server that can now focus on generating dynamic content. Secondly, we want to use CloudFront, that is a content delivery network. CloudFront can reduce latency for your users around the world by caching both static and dynamic content on the edge locations around the world. In some cases, even a few seconds of caching for very popular pages can result in huge reduction of load for your web server. But also for non-cacheable content, CloudFront is going to provide network optimizations. So what we are doing here is using CloudFront to serve the whole application. We can specify a different origin depending on the specific file path patterns. As you can see in this example, we are using S3 for static content and EC2 for dynamic content. Next, we can apply caching on another layer. Any frequent queries to the database, where the results do not change very often, can have their results cached and served from an in-memory cache. This is going to provide a better experience and reduce the load on the database. You can, of course, install memcached or Redis, which are popular solutions for caching, on a set of EC2 instances. But like what we mentioned before for the database, again, you can use a managed service for that. And this is Elastic Cache on AWS that allows you to run those engines without the operational overhead. Okay, so now we're done with the beta version. We have refined the product, but we want to get more sincere feedback and iterate fast. The best way to get good quality feedback is by offering paid membership of some sort. It is now very important that we introduce high availability in the architecture. A hardware failure should not impact the end users. And here is the current architecture, which, as you can see, has multiple single points of failure. For example, if the web server crashes, the application will stop working. To fix that, we add a second web server from the same AMI, but on a separate availability zone. Each AWS region has multiple availability zones that are physically distinct locations. This allows you to build extremely robust architectures that utilize multiple data centers. Because we have multiple web servers, we now need to distribute HTTP requests with Elastic Load Balancing. And Elastic Load Balancer is not a single server. It is itself a managed and fault-tolerant service. Elastic Load Balancing can be configured to stop sending traffic to a non-healthy web server so that your users do not notice the issue. Elastic Load Balancing will also automatically scale its own capacity to process incoming requests depending on the traffic. For the database, assuming we are using RDS, we can enable the multi-AZ feature. The multi-AZ feature is going to launch a secondary node in a different availability zone. In an event of failure of the primary node, RDS is going to automatically fail over to the secondary instance, maintaining the host name so that you don't need to manually modify your application configuration. Similarly, for the cache, we want to expand it to multiple availability zones. So we add a second node of Elastic Cache. If you're using Memcache, each of those nodes stores a portion of the keys, so the impact of failure is reduced. In the case of Redis, we can even configure a master-slave replication and automatic failover with Elastic Cache. Now, a problem that we're going to face when moving from a single server to multiple servers is how are we going to manage user sessions? Typically, most runtime environments store those on the local file system, which is not a shared resource. So we can have the scenario where a user signs in on one server, but will be logged out on a subsequent HTTP request that happens to be serviced by server 2. A quick fix here is to use ELB feature called session stickiness. This is going to send a particular user to the same backend server every time. We're going to see later on why this is not our long-term solution and why it is better to move session storage to DynamoDB. DynamoDB is a managed NoSQL data store on AWS that stores your data durably in multiple availability zones. It also has consistently fast performance, so this makes it ideal for the storage of session data. In fact, for PHP and Tomcat environments, there are drop-in replacement session handlers that you can use to achieve that. Now, moving on to the journey of our startup, let's assume that we have seen some good traction and we are now ready to invest on marketing campaigns, which could help us go viral. In traditional hosting environments, this is a nice but difficult problem to have. You would need to guess how many servers to buy or rent, and you might order too many or too few. In AWS, you can go to the console and add more web servers when you need them. For example, you can add 2 more servers and attach them to the Elastic Load Balancing service. Elastic Load Balancing itself is going to scale automatically. But this is not something that you want to do manually, because even during the same day, you might have a variance in your capacity requirements. So you want to automatically adjust the number of servers in your fleet to be as close as possible to your actual needs. Autoscaling on AWS is a service that allows you to do exactly that. You configure a minimum and a maximum number of servers, and you set a rule that defines when you want to add more servers or when you want to remove servers. For example, add more servers when CPU utilization is high for more than 5 minutes. And a great example here is the story of one of our customers, a startup called Animoto. They make it easy to create and share videos with friends and family. And the team at Animoto started with a few servers, but they had to scale massively when they launched their Facebook integration feature. They were able to scale to a peak of 3,500 servers in just 3 days. They did not have to do much about it because they had autoscaling set up. Now, we do set default limits on new accounts on how many instances you can launch in parallel, so make sure that you submit a limit increase form in advance. You can do that through the website. This sounds very easy, and it is, as long as you have a stateless architecture on your web servers. But what does a statelet architecture mean? It means that anything that needs to persist beyond the lifetime of a single HTTP request should be stored in a shared storage, not on the web server local storage itself. In our example, we have already done the hard work. We store user uploads on S3 and user sessions on DynamoDB, and everything else persists on the RDS database. Having done that, we can simply add more servers when we need them. But more importantly, we can terminate any of them at any point in time. None of them stores any important data that I have not stored elsewhere. And this architecture that I described is simple, but deploying it manually is not the best way. Obviously, you need to learn about AWS autoscaling, deploy your application to multiple servers, maintain different environments for development, testing, and production, and multiple versions of your application. Maybe you also want to do A/B testing and you want to have 2 parallel environments running at the same time. You will be able to move a lot faster and hide some complexity by using an automated service like Elastic Beanstalk on AWS. An Elastic Beanstalk allows you to provide your code as a zip file, and the service will configure elastic load balancing, launch servers in autoscaling, and deploy your application code. It is a free service, and you only pay for the resources it launches on your behalf. It supports multiple runtimes, as you can see on this slide, from .NET, PHP, Java, to Node.js, Python, Ruby, and Docker. It is also very customizable. You can have a lot of control on the exact configuration of those runtime environments. Another useful pattern when dealing with spikes of traffic is that of loose coupling. Here is an example. A user submits a request that kickstarts a complex backend process. Perhaps the user does not really need to wait for that to happen. In that case, we can place that request in a queue, and we can process it asynchronously at our own pace. SQS is a managed AWS service that you can use for that. It will result in a faster experience for your end users, but also give your backend breathing room as it can process those events at its own pace based on its capacity at any point in time. A few days ago, the AWS Lambda service became also available. This is another way to offload asynchronous or synchronous tasks to a managed execution layer that you don't have to manage and scale. And now that we have many users, it is important that we increase our pace and add new features very quickly. Many times when you want to add functionality, you might need to introduce new components to your architecture. Perhaps you want to implement advanced search features, so you might need a search cluster. Or you want to send push notifications, or you want to implement video transcoding. In those cases, your first question should always be whether there is an AWS service that already achieves that, and it is designed already to scale instead of figuring out on your own how to implement this on EC2. And it is important to realize that those higher level services, think of them as building blocks, are already implemented to scale so that you don't have to worry about their architecture. In fact, some of those will do this automatically for you. On the other hand, we have seen how services like EC2 give you the freedom to architect in many different ways, so your architecture and your application needs to be built in a certain way to take advantage of the elasticity of those services. Those services are available with a few clicks, and as long as you can use such services, you can keep the size of your team small and still achieve great outcomes for your customers. Even later, if you have lots of revenue and you can hire many engineers, it is always better if their focus is on the things that differentiate you and your application, not how to manage, for example, a search cluster. Now let's assume that the startup is growing fast, adding a lot more users. More users means more data and a lot more queries for the database. So let's tackle one of the hardest problems. How do we scale the database? We started with the relational database. So what are our options here? We can obviously add more and faster storage or move to a larger server on RDS with just a few clicks. But in terms of read capacity, we can scale beyond the limits of a single database server. This happens via the use of read replicas. These are additional servers that hold asynchronous copies of your data. On RDS, this is available for MySQL and PostgreSQL. Now, the write queries will still need to be performed against the master node. But any read queries that don't require strong consistency can be spread across multiple read replicas. Just be aware that there is a small replication lag, so queries that need strong consistency will still need to be executed on the primary node. So going back to our architecture diagram, we can add one or more read replicas. And again, it is a good practice to spread those in multiple availability zones. There will be use cases that will be very write heavy. Or perhaps you want to store many terabytes of data. So as you grow, you will potentially end with a limit on the largest RDS instance that you might have available for you. And there are two solutions here. One is to federate the data. Perhaps you can split your databases by function. Let's say that you have a forum application and you can move it to its own database. This can help in many ways, but in some cases you will have single very large database tables. For those, we will need a different technique. We will need to use sharding. A database shard is a partition of the data. Each partition can be hosted on a separate database server. For example, we can partition our user data based on their user ID. This is a great pattern for multi-tenant applications where you never need to perform joins between, for example, one customer and other customers. But sharding adds complexity as it needs to be implemented in your application logic. Another option is to move those workloads to a NoSQL data store that is designed to handle sharding automatically for you. NoSQL databases typically trade some of the query capabilities and integrity checking properties of a relational database. On Exchange, they give you a much more flexible data model that can scale horizontally. This is what allows DynamoDB to provide you with two simple configuration options: how many reads and how many writes you want to support per second. It is a fully managed service, and all the partitioning happens automatically on the background, either because your dataset grows or because you tell us you want to provision more capacity in terms of reads and writes per second. If we follow the same concepts, we can keep on scaling with no practical limits. We can add more web servers, more caching nodes, more read replicas, and we can move the right database workloads to NoSQL. We can also take advantage of all those higher level application services on AWS. As a summary, you want to keep things as simple as possible and create a stateless web architecture. If you're running your own EC2 infrastructure, you want to distribute it across multiple AZs and use auto-scaling. Do try to use managed services on AWS as much as possible, and of course select the right database for the right job. Caching is very important to help you be as efficient as possible, and you can try and use automated deployment tools, for example, the Elastic Beanstalk service that we mentioned before. In terms of next steps, there is a lot of documentation online, but also I would like to highly recommend that you sign up for AWS Business Support, as it can really be an extension of your startup team. Of course, don't forget to sign up for AWS Activate, which is a program designed specifically for startups. And with that, I would like to welcome Peter from Just Eat.
Hi, I'm Peter Mounce. I'm an engineer at Just Eat, and I've been there for more than 5 years now. Just Eat do online takeaway. We're the online sales channel for partner restaurants. We operate a mostly .NET stack hosted on Windows, running at scale. What's that mean? About 70 searches per second at the top of the funnel, about 1,200 orders per minute at the tip of the funnel. We're a cloud native in AWS and have been for about 2 and a bit years, and we continuously deliver the platform, doing several deploys a day. The restaurants have a little magic box inside the restaurant listening to our system, and that's how they receive the orders. If you've ever paid for a takeaway online with Just Eat, you've run through my code. I worked on the payments part of the flow, and nobody's managed to delete that quite yet. The demo gods are not with me particularly at the moment, so I won't show this live. But what I would have shown is starting off some of these fake load jobs against our production environment. As you can see, they're exercising different parts of the system, and they're at different levels to simulate different load levels through the week. And then we use this graphite dashboard to figure out how we're doing. So you can see the top left over here, blue line is the fake load that wraps up over time, and the green line is the real customer load running through our system. And then we do things like track the request counts and the CPU counts and that sort of thing through the rest of the platform. The classic problem with performance tests and continuous delivery is that performance tests take a long time, and you don't want to sacrifice continuous delivery in decoupled teams. You've got all the usual problems if you've got a single performance test environment. You bottleneck through it, so nobody owns it, so it's always out of date, so you waste time. Everybody wants it, so it's never available, so you waste time. It costs too much to duplicate production, so it's not the same, so you waste time. Then you've got individual performance tests that take too long, so you waste time. You generally want to soak your environment test for an hour at least. You want to stress test, so by design things will break, so you have to put them back together again. You've got engineers that won't wait for a long-running test because, well, it's boring. So when they come back and they notice it failed at 5 minutes in of a 60-minute test, they have to figure out why it failed and then set it up again and rerun it. So you waste time. We don't want to waste time. So we want continuous assurance of both performance and capacity. Still delivery. We also want to be nice to the personal time. So if we find a problem on Thursday night, we don't want to decide to stop fake load over the weekend, so we don't have that problem on the weekend. We enjoy the weekend as normal, and we fix it next week at our leisure. So I swear I overheard this at the office. I bet if we deploy tens of changes a day and they're small, we won't break production. Let's just do it in production with fake traffic at the same time as customers. What could possibly go wrong? It's not that much of a gamble, as it turns out. We've got quite tight feedback loops in place. We've got engineers that are highly invested in not regressing performance because they're on call. They'll get the alert in their personal time. But we support them in this. Engineers own their own code, support it directly. We've got near real-time monitoring with alerting. We've got centralized logs to figure out what happened. We've got the engineers that get alerts, so they'll be right in the midst of the problem if there's a problem. We've got engineers that can turn off fake load really easily to buy themselves time to think about what might be going on. And we've got engineers that can perform rollbacks quickly. So it turns out to not actually be a problem to do our testing. We haven't had a regression in the last year that we didn't notice on the same day it was deployed. For us, has been good enough. So how do we do this? We pick the scenarios we care about. So for us, that's customer can place orders, because that's where the money comes from for us. So that means that a customer must be able to search for restaurants, choose one, view the menu, pick items from the menu to put into the basket, then check out either with cash or with an online payment. We use JMeter to record the scenarios. JMeter is an arbitrary choice. We could have used Gatling, some Grinder, or something else. We're pretty happy with JMeter. We then also inject data variation and randomness. So rather than just having one test load user restaurant, we have thousands. And then we do things like add headers to our fake load so we can discriminate it from customer load. One of the things this lets us do is not involve our real payment providers in the fake load, because that would cost too much and they wouldn't appreciate it. So we wrote a little test harness to respond like the payment providers do, and fake load goes there rather than to the real one. We also fake away the physical boxes in our restaurants so that the cooks don't ship the fake orders. The other part to how we do this is we run it every night, during peak time, in production. And if no alerts fire, we're good. What do we gain with all of this? We've got continuous confidence in our capacity without doing any manual work. Basically, we turn a Thursday night into a Saturday night so we can know we're good for the weekend. We turn a Saturday night into a Saturday 6 months from now, according to forecasts, so we know if we're good for later. We've got a seasonal business, so later is different depending on what time of the year you're at, but it comes out in the wash. We've got continuous confidence dealing with spikes. So spikes could be viral marketing or denial of service attacks like the one I'm currently running against our production environment now. But basically what this means is we can turn off fake load, and we know we've got that much headroom to deal with spikes. And so the first operational response when an engineer is bleary-eyed from responding to the sad trombone alert is fake load running, turn it off, and then start thinking. We've also got performance as a first-class concern. Nobody wants to receive an alert in their personal time. There's a difference between being ready for production versus being ready for customers. We therefore have engineers that push back on releasing until they're satisfied that it will perform as well as just function. The make it work, make it good, make it quick mantra is baked in. So performance profiling happens before being in production for customers as opposed to just being in production. And then we have alerts that are just automated tests that run in production. Another benefit is tests can become independent of data in a particular environment. It means that for tests to pass, we don't need to have the database to be in a particular state. Features can return stub responses, so host some static JSON files, for example, in an API, and the logic in the API can use the header to discriminate whether to return an actual processed response or whether to just return the static response. This lets teams decouple with respect to integration tests. Classically, you agree the contracts and go independent and don't change the contracts, and so you can develop in parallel, you can deliver in parallel. And then once both teams have got their stuff in place, turn it on with a feature toggle. This enables us to speed up delivery quite dramatically. So if this were a demo, then I'd be stopping my DOS attack now and I'll be showing you the dashboards, but this isn't. So just like every other AWS customer that's taking the opportunity to speak, we're recruiting too. You can find out more about what we do on a day-to-day basis engineering-wise at our blog, which is tech.justeat.com with a hyphen. And you can also find out what jobs we're currently recruiting for. We're always recruiting at tech.justeat.com/jobs. Thanks very much.
Thank you for joining us for this session from the AWS Summit London 2015. We really appreciate you giving us your time to learn more about Amazon Web Services. If you want to stay up to date with new AWS services and other AWS news, please follow us on Twitter at AWS Cloud. You can also stay up to date with the latest news from AWS here in the UK and Ireland at AWS UKI on Twitter. If you want to continue to learn more about AWS, you might also be interested in the regular webinars that we are running through 2015. You can find more details on these in the video description for this video. You can also find a link to the slides from this session on SlideShare in the video description, and you can download a PDF version on the slides from there. Thanks again for joining us.